Thank you for the introduction, and thank you to Alex and Sean for all work putting this together and for inviting me. I'm really excited to be here and to be talking about this. So I'm going to be talking today about conjectures for distributions of class groups when there are roots of unity in the base field, and everything I talk about is joint work with Will Solin. Okay, so I'm going to begin with just saying something about the Cohen-Lenstra-Martinet heuristics. So in 1984, Cohen and Lenstra gave conjectural distributions for class groups of quadratic, either real or separately complex extensions, and of totally real abelian extensions for every abelian group A of the rational numbers. And these conjectures have been hugely influential, and it is a real honor to be talking about them with Ari and Hendrik here in the audience, because they have been a source of a ton of beautiful mathematics that I have really enjoyed thinking about over the years. So the idea is just, this very important invariant the class group of a number field. What do they actually look like if you go out there and look at them? Like what groups do you see? What is out there in the universe? And in 1990, Cohen and Martinet extended these conjectures for distributions of class groups of G extensions for arbitrary finite group G of an arbitrary number field, and then similarly with some specified behavior at the infinite places. Oh, and that should have been of K0 of the base field. Okay, and I'm going to give an example just to set the stage. So for an odd prime P, let's say you range over positive fundamental discriminants, the conjectural probability from Cohen and Lenstra's paper in 1984 that the CeLO P subgroup, so I write here like the P to the infinity torsion for the CeLO P subgroup of the class group is isomorphic to some A, some finite abelian P group A, is this precise number. Okay, so that doesn't depend on A, that's just a constant. So that when you sum this expression up over all A, you get 1, and the size of A and the size of the automorphism group. And this example will set the stage for how imprecise I'm going to be about what I actually mean by ranging over in the conjectural probability. Here you should take discriminant up to X, and then you pick one uniformly and let X go to infinity. I'm not going to worry about any of those issues today, even though there are some very serious and interesting issues to worry about. I'm just going to focus on what what these numbers should actually be, if you set up the question right. And so these predictions, for example, these numbers show remarkably good agreement with the data, and I mean, in fact, were originally conjectured because of observed patterns in the data, but Malle was doing more and more computations of class groups of number fields, and around 2008 and 2010, among the extensive computational data on class group distributions that he was considering, a good deal of which, in many cases, gave very good empirical evidence for the conjecture, there were some irregularities. And so this is a chart of the average size of the elementary abelian P part of the class group. So this is like the P torsion, and this is of C3 fields. So this is abelian cyclic degree 3 fields. And so in this chart, to read it, so this is discriminant up to these various bounds. And here, this is an exhaustive search. And here, this is just 10 to the 5th sample fields from discriminant, just bigger than this. Okay, and then here we see for each prime, this is as the discriminants are getting bigger and bigger, you're seeing some convergence in the absolute size of the average p torsion, and then this is the prediction of Cohen and Lenstra, and you see here very good agreement in all of these cases, except for this one. And not only is it off, but it really looks like it's going to another value there, right? As Malle looked at more and more cases, he realized that the being off by 2 had to do with roots of unity and the fact that Q, when we're taking C3 fields, they're extensions of Q, has 2 roots of unity in it, and that's why there's a sort of problem at 2. And based on his data, so let me give you the C3 case. So Cohen and Lenstra had conjectured that the probability that a C3 extension of Q has class group with 2 rank 2R. You can think a little bit of why the 2 rank, it always has to be even. And this is some specific, what the formula is. So on the top, that's a constant. These 2 products depend a little bit on R, and this somehow in R, the main term here is this 4 to the R plus 1. But based on his computations, Malle conjectured instead the probability that your class group has 2 rank 2R should be this. So this is another number. Again, the top is a constant, so that's like what you have to put there. So should everything else adds up to 1. This term on the right is also a constant, but then there is one factor that depends on R. And you can see that the main term is quite different in R, right? It's going like R squared over 2 somehow in R. So Malle conjectured this probability instead, and this gives much better agreement with the data. This here, so this formula 1 is Malle's, and so if you look at the probability that you have 2 ranks, so this is the probability 2 ranks 0, 2, 4, 8, and then these are averages of that. And this n equals 1 is that average we were seeing here before. You can see that this corrected formula it gives very good agreement with the data. And so this was just one situation, C3 extensions of Q and the 2-part. And so since then, people have tried to make various conjectures to correct for roots of unity in the base field and to adjust the Cohen-Lenstra-Martinet predictions in that case to give something that matches the empirical evidence. So in 2008 and 2010, Malle gave further conjectures, including that one that I had on the last slide, for a handful of Galois groups, always only with P, but not P squared roots of unity in the base field, which is fine if your base field is Q, and then you have just two roots of unity, but not 4. And in 2015, Adam and Malle gave conjectures for a few more Galois groups, and they allowed any amount of roots of unity in the base field, but they didn't actually give an explicit conjecture for, not like that probability formula that we saw in the last slide. They instead gave a conjecture that the probability of the class groups should agree with the limit of a certain distribution coming from random matrices. But they didn't have formulas for that probability distribution arising from random matrices, and in fact, didn't even prove that the limit existed. I mean, partially maybe because they didn't have formulas, so they didn't really have a good way of proving that the limit existed. And then in 2020, Lemnowski, Sahn, and Zimmerman, they gave a conjecture for quadratic extensions. So this is just the Galois group C2, and they gave explicit formulas for the distribution with any number of roots of unity in the base field. So you could have, this would be like, okay, quadratic extensions of a base field that contains 27th but not 81st roots of unity, and you want to know what the 3-part looks like. They give explicit formulas for it. So in this work that I'm talking about today, which, like I said, is joint with Will Sahn, our goal was to give corrections for all Galois groups G when you're looking at G extensions and the distribution of class groups of G extensions, and for any amount of roots of unity. So for any Galois group G, you want to look at Galois G extensions, look at their class groups. What you specify what roots of unity you have in the base field, and we want to give a conjectural distribution for the class groups that you'll see. And we want those to be explicit formulas. We want to write down for you a formula. Say for any prime that doesn't divide the order of the Galois group, because that primes dividing the order of the Galois group provide a new sort of complication. Eventually, one hopes to deal with that. But for today, for any prime that doesn't divide the order of the Galois group, we'd like to give a conjectural distribution for the CeLO P subgroup of the class group distribution among G extensions. Okay, so how we are doing this, our starting point is a theorem in the function field analog, even though these conjectures were originally about extensions of number fields. One imagines both such things. We should also hold for function fields. And in function fields, we have other tools, algebraic geometry over FQ tools, that we can use to sometimes see some pieces of something that we can't see in the number field case. And so following from work of mine with Yuan Liu and David Zerg-Brown, we show that in some limit as little q goes to infinity, if I'm now taking extensions of FQT, so the function field over the finite field FQ, and so one thing you already can't do in the number field case is take some kind of q goes to infinity, and I'm taking extensions varying over, say, G extensions split completely at infinity, then for every finite G module with trivial invariance, I get some average. All right, so let's parse this out. So this expected value, that's an E for expected value. I'm taking the average over the extensions. So I'm varying over G extensions. And again, I'm going to be a little imprecise about how you should vary over G extensions, because that's not the point of this talk. And then I'm counting surjections from the class group to H, but I'm counting G module surjections, because if I have, of course, a G extension, then the class group is not just an abelian group, but it is a G module. And so it's reasonable to think about that structure. And so this is the average number of G module surjections from the class group to H. And this average goes, there's two limits here. There's some kind of limit as you're varying over extensions, and also a limit as Q goes to infinity. And then here I have two things. So the denominator is simple, it's the size of H. And in the numerator, I have some size of some group, but I only take the part of it. I've written it in this awkward way to emphasize that the part that I take depends on the order of the group of roots of unity in the base field. So this, in this case, when you have FQ, then they're just Q minus 1 roots of unity. So that's a funny way of writing Q minus 1. But I wanted to really emphasize that what's happening is there's some group, and I take the torsion in it, and the amount of torsion I take depends on the order of the group of roots of unity in the base field. And what is this group here? So I take the exterior power of H as a Z module, and I take the G invariance. So this is just like, you think of G as think of H as a representation of G, then I'm just sort of, taking the invariance. So this is no longer, of course, a G module, or it's only a trivial one. I've taken G invariance. And so that's some group, and I take some torsion that's based on roots of unity in the base field. All right. So because something, doing algebraic geometry and investigating certain moduli spaces of covers over FQ allows us to see a result like this. These averages we consider as moments of a distribution of G modules. And I'll say a little bit, we'll be talking more about that later. But for now, you can just think about, that's what I'm calling these averages, number of surjections, are moments. And so we show that these moments these averages, so I'm looking for some distribution on the class groups, and these are different averages over that distribution, right? The average number of surjections to this H, the average number of surjections to this H. And we show that those averages determine a unique distribution of G modules that can be given explicitly. So from these numbers, from these averages, the average number of surjections you have to H for each H, we show that you can give explicitly formulas for how often you are every particular G module.
Sorry, Melanie, I missed.
Yes.
What do these square brackets denote?
Taking the torsion, like the intorsion. Yeah, maybe I should have like wrote that as a U or something, but I wanted to really emphasize that it was the number of roots of unity. But if like N is the number of roots of unity, I'm taking the size of the N torsion in that group. Thank you. Yes.
In this theorem, if you replaced FQT with like another function field over FQ and like took a limit as powers of Q going to infinity, do you think the same?
You mean a function field of another curve?
Yeah, another higher genus curve.
Yeah, I don't. Yeah, so I don't think that. I mean, I think that is a that is a thing that is in like reasonable to imagine someone doing, but has definitely not been done. Yeah, so I think that is.
But you expect the answer to be?
Well, okay, except that it. Ish, right? What's the ish is that I'm sweeping a few things under the rug here because it's a function field and I wrote okay, which point on my curve, as we saw in Bjorn's talk, like you have some choice when you make an affine curve what points you throw out, and if you throw out more curves you'd have a bigger factor, more points you'd have a bigger factor here, but okay. But essentially there'd be a slight variation of this formula depending on how exactly you made your affine curve. Thank you. Other questions?
So in the same
Yes.
vein, if you weaken the split completely and instead ask for other real signatures at infinity, you have to keep track of a transposition or something, or
Yeah, so if you ask for other behavior at infinity, what one expects is this thing, this will change a little bit because your behavior at infinity is not just a number, it has to do with G. It has to do with what representations of G are you seeing at infinity in the decomposition group at infinity. And then H is really secretly composed of all the different pieces for different irreducible representations. And so what appears in the denominator will be powers of those pieces of H, but that will depend, the exponent of that you take each of those pieces to will depend on the behavior at infinity. Yes.
I think I might just be confused about orders of quantifiers.
Yes.
But in the numerator of that expression,
Yes.
Q is going to infinity?
Okay, fair. All right. All right. So one thing you could do is you could just divide by it over here, and then you don't have that problem.
Well, but I'm also just wondering what does the Q-1 torsion of this module look like when Q goes to infinity?
Okay. Well, all right. So I'm going to give you two different things to answer your question. The first thing is you simply could take this expression and you could move it over here and put it in the denominator. And now it's just, then this would just be a number for each Q. And I'm saying those numbers go to 1 over H. Or you could alternatively for each H, right? H only has some finite exponent. So all you really care about to know about the size of the Q-1 torsion is what common factors Q-1 has with H. So if you take only Qs that have some fixed common GCD with the order of H and Q-1, then Q can go to infinity through those. And then, I wrote it this way because we're really interested in the question where Q is fixed. And that's the analog of the number field situation. And even though we can't prove a theorem like that, this is kind of the shape of the theorem that we're interested in. So I sort of cheated how I wrote it like that. Good questions. Questions? All right. So let me say, all right, so our conjecture, just to be precise about it, when G is a finite group and P doesn't divide G, if you have a number field K0 with U infinite places, and say it contains the P to the rth roots of unity, but not the P to the R plus first roots of unity for some R, so that there are actually roots of unity there. Otherwise, if R was 0, then we expect that the Cohen-Lenstra-Martinet original conjecture holds. And we're going to take a relative class group. So for these P's, for P's that divide the order of G, there could be some subtlety in what you mean by the relative class group. But when P doesn't divide the order of G, all the notions are the same, and I'll just take some simple one. If I have some extension of K0 and K0 has some class group, then it's not very interesting. Somehow that can contribute to the class groups of all extensions of K0. So I'm interested in the part that does not come from the class group of the base field. So I could just take the quotient, say the class group of K0 just maps to the class group of K. So I could just take the quotient group and take the CeeLo P subgroup of that. It's equivalent to just take the piece that is to get rid of the invariant piece under the Galois action. That's equivalent here again, because P doesn't divide G. And so for these relative class groups, all right, so we conjecture that the distribution on invariant free G modules, and I say invariant free because, like I said, getting rid of the class group of the base field is exactly equivalent to getting rid of the Galois invariance, will be the one who has precisely these averages for every H. So the average number of surjections onto H should be this here. And so here you now see, and this is maybe easier to parse, I'm taking the P to the R torsion in this group, where P to the R was the number of roots of unity that I had. And I have H to the U in the denominator, where U is the number of infinite places. All right. So, and like I said, among what we show is that that if there is a distribution, that there's only one distribution that you can reach in the limit if you have these averages in the limit, and we give that explicitly. So that's what I'm gonna give explicit formulas for this distribution. All right, yes, we give explicit formula. So let me give you an example. So example G equals C7. So let's take just the rationals, which have 2 roots of unity, but not 4. So P equals 2. And there are 2 non-trivial representations of C7 mod 2. So a G module has a rank for each of these. So instead of thinking of a 2 rank of a group, you should really think of like a rank for each of the 2 irreducible representations mod 2. This is going to be about like a 2 group representation of G. So for a V with ranks A1 and A2 for the 2 non-trivial representations of G, we conjecture that the probability that the CeeLo2 subgroup of a C7 field is isomorphic to V is this following expression here. All right, so we have the ranks there. So we have the size of V and the size of the automorphism groups of V, and then we have this A to the A1 times A2, and we have some products, and then we have this last product here, which note that it is sometimes 0. It is sometimes 0. So this was an example. This is just an example for one group. And now in general, the formulas involve all of the non-trivial irreducible representations VI of G mod P. So they get more complicated because there are more representations. But this gives you a sense of what they look like. I'm going to show you one more like big formula, but so here's what the general conjecture looks like, but just on the P torsion. So this was for the whole CeeLo2 subgroup. This gave you a complete formula for the whole CeeLo2 subgroup. And the next one is going to be just for the P torsion, because if I do like a general group and I do the CeeLo P, it really can't fit on one slide. All right, so you need to know about the representation. So those VIs are the irreducible representations of G mod P, and if QI are the size of the endomorphism fields, because these might not be absolutely irreducible representations. So they might have, and then you take the dimensions of the representation or of the absolutely irreducible components or whatever. The size of VI is QI to the NI for some NI, you get those numbers. And then if epsilon I for each representation is what people call the Frobenius-Schur indicator, it tells you basically whether a function, or sorry, whether a representation is not self-dual, or if it's self-dual, if it's symmetrically self-dual or alternatingly self-dual. There's two ways for representation to be self-dual. Then we, all of these numbers come into the formula. That's why, I have to give them all names. So among G extensions, for every representation that is self-dual, the P torsion is isomorphic to V with probability here. So you see here, still what looks like those moments here, right? The size of the second wedge power G invariance and the V to the U and the automorphism, and then some other factor, and you see that the Frobenius-Schur indicator, like what kind of self-dual representation you are, and the NIs, the dimensions come into these formulas, but this is a constant that doesn't depend on V. This is the dependence on V is in this expression. Yes.
Sorry, Melanie, what signature the case?
Well, because this is we greatly simplifies things. So they're always split completely at infinite places, because if you have Pth roots of unity, either your base field is totally complex, in which case you're always split at infinity, or you could only have P equals 2, and then when P equals 2, you're only looking at odd degree extensions, and those also have to be split completely at infinity. So we have cleverly, it turns out that everything, all the extensions have to be split completely at infinity once, because as I said, either you start with a totally complex field, or P is 2, and then you're only taking odd degree extensions. Yeah. So that's why this V to the U is a little simpler than like what I was suggesting to John, like the general case would look like. Because the condition of imposing the roots of unity in your base field in the number field case imposes some conditions on what can happen at infinity. All right, and then let's say you have two dual representations, so two different irreducible representations that are dual of G mod P. So then the probability that your say Fi copies of one and Fj copies of the other is this expression. And I had to write the Fi Fj here because they actually appear in these formulas. And notice I say if the difference between Fi and Fj is at most UN minus 1, and it's 0 otherwise. So we conjecture that certain, that basically if your ranks of your dual representations are close, then you see that those class groups a positive probability of the time. But if they're too far away, depending on the numerics of the situation, then with probability 0, you see class groups that have the VI and VJ components. So representation, and it's an irreducible representation, and it's dual sort of far away, it should be 0. So I really want to emphasize here the behavior of the dual representations is really not independent. I mean, this is like the starkest way in which it's not independent. We say that, like, based on the number of copies you have of one representation, there are some numbers that are impossible. But even if you somehow restrict to the possible ones, because of this, which is kind of like the 8 to the A1, A2 in that C7 formula, even it's not some probability distribution that was independent on the two factors that was then restricted to what's possible, because there's a dependence here. If I want G invariance, however many copies of a representation and then its dual I have is really affecting my number of G invariance. I mean, it's basically just the, like this is, it would be the product of Fi and Fj is how much I will see in this top factor here. And so in particular, we're suggesting in this, at least in this probabilistic sense here, that some G modules never occur. And so these 2 points were not in any of the original conjectures of Cohen-Lenstra-Martinet or Malle. So I said, Malle had given a few cases here. This phenomena, in all the previous conjectures, the behavior was predicted to be independent of every different G representation mod P, that the behavior you saw at each G representation should just be independent, and you just multiply them together to get the final answer. And we predict that some G modules never occur. And so this had phenomena, I should say, had been seen in recent work of Neil Varma and John Voigt in some of their work on class group distributions, and they had realized that these 2 facts were happening. Okay. And so, in fact, for all the G modules that we conjecture occur with probability 0, we do, in fact, prove that they never occur. So that just back up, and we realize, oh, there's this question here: which modules can occur? So if you have a prime, which G modules can occur as a relative class group? And so I'm taking the CLP subgroup, so that's why I wrote a ZPG module. And then I took the quotient by what's essentially like the idempotent for the trivial representation, because when I'm taking this relative class group, as I said, I've gotten rid of, when I get rid of the class group of the base field, I've got rid of the invariant part. So the relative class group should be a module for this group ring. It has no copies of the trivial representation. That's what that quotient is about. And all right, there are some finite, that we know what all the finite for P not dividing G, we know very well what all the finite modules are, and we could ask which ones occur. Okay, and so I'm going to use a notion here, P to the L rank of a finite abelian P group A. It's like the dimension of the P to the L torsion minus the quotiented out by the P to the L minus 1 torsion. So that sort of tells you layer by layer, like what your finite abelian group looks like. So we show that when G is a finite group and P dividing not a prime, and if K0 has U infinite places and contains the P to the Rth roots of unity, and when you have a Galois G extension, then for every pair of distinct dual irreducible representations of G over Fp, all right, I'm just putting in all the things we need to talk about it of dimension Dn with idempotence EIJ in the group ring and splitting field of degree D. So this is an inequality between P to the L ranks. And this EI is because I'm picking out the part of the relative class group that corresponds to one of the dual representations, and this EJ picks out the part of the class group that corresponds to the other dual representation. So in this class group, it all because P doesn't divide G, it all breaks down with idempotence from the group algebra in all the different irreducible representations. And I'm saying that these ranks can only be so far apart. And I wrote this in this weird way where the Dn is in parentheses, because the Dn is the dimension of the irreducible representation. So we know that these ranks are multiples of Dn, because I wrote them as ranks like this. But all right, so these are ranks, as I said, dimensions over Fp, just for simplicity. So if we were counting multiplicities of the representations, they differ by at most UN. So we prove that, and this is a fact for P to the L ranks for L going from 1 to R. So this says that based on having roots of unity in your base field, there are just certain kinds of class groups that you can't, that can't occur ever. So special cases of this result were due to Leopold and Gras in 1958 and 1998. And I do want to say that, so over function fields, if we just say function fields generally, this is as strong as possible in that our theorem over function fields combined with our theorems about what the averages tell you about the distribution, says that every possibility that is not eliminated here does occur over function fields. And so this is a completely, this theorem is not a probabilistic theorem. This is just about what can even possibly be the G module structure of a class group. And we do conjecture that everything that it satisfies this inequality happens with positive probability. So we certainly conjecture and expect this to be the strongest possible result over number fields. And honestly, I will say that once we knew that this was the result that we were trying to prove, the proof of this is not so hard. And so what really was new here was realizing that this was the result that we wanted to prove. And we realized that by being able to compute probabilities in the, from the function field moments to compute probabilities, and then we compute them and see some of them are zero. And once we see that some things are zero, then we think, oh, maybe there would be a reason for this. And so in these special cases of Leopold and Grad, they had seen, okay, for some reason, something, is happening here, some reason something is happening here. But what really enabled this to happen, to get what I expect here to be sort of a complete statement of the restriction on what can be the class group as a G module, came from having these exact formulas that came from the function field moments and being able to detect whether they were zero or not. And so when I said, we wanted to give explicit formulas, one of the things that I really want out of my explicit formula is I want to know whether it's zero or not. And as you could see in those formulas that I gave before, it was, we said exactly what they were, and they're these products, and then you can really see when they're zero and non-zero. Okay, so let me say something about empirical evidence. So I will say, our conjectures do not agree with all of the previous conjectures. So Malle, I said, had made a bunch of conjectures in different special cases for a certain G, but we do agree with all of the conjectures of Malle's for which he had empirical evidence. So I think that's a very good sign. But, I think he was sort of guessing some extensions based on sort of patterns in the behavior. And, there's can be different patterns can sort of extrapolate in different ways. And here's an interesting case where actually there was no previous corrected conjecture. So this is a table showing data. This is Malle's data. The first three or four lines are Malle's data. So these are on C3 extensions, so cyclic degree 3 extensions over Q adjoin I. So there's fourth roots of unity in the base field, not just second. So this is the original conjecture, which doesn't factor in any roots of unity in the base field. And this is Malle's conjecture for when you have 2 but not 4 roots of unity in the base field, is what this line is here. But he didn't conjecture. He was like, clearly you need to do something else when you have 4th roots of unity. So this wasn't a conjecture of Malle's. He's like, he didn't know what you should do, but he's like, you need something different. And our conjecture gives, as you see, these numbers that are in very good agreement with the data, but came completely independently from the data. They came from this function field perspective. But there are a lot of cases where more empirical data would be interesting. The C11 case, for example, just over the rationals, is a case where Malle gives a different conjecture than we do. Of course, I believe in our conjecture, that's why we made it, but it would be interesting to see what the data look like. And I just put up a few cases that, these are cases that have some interesting feature, like the C4 over zeta 5. This degree 4 D4 over Q adjoin zeta 3 has these dual representations and is not P equals 2. You know, sometimes people think, well, maybe P equals 2 is a little different, you know, okay, so this is a good case that has dual representations and P isn't 2. Yeah, so I think it would be very interesting to look at these cases and to look at other cases. That's sort of how this whole field has gone all along, has been through looking at a lot of empirical data, seeing patterns, trying to describe it, having more data. So it would be good to see if these cases back up this, especially this function field, number field analogy that we're making. All right, so now I want to get into how we, you know, what is going on with going from these averages to these distributions. And this comes from another piece of work on the moment problem. So let me just sort of go back and what do I mean by these moments? So this is the context in which I'm thinking about these moments. It is a classical and important fact in probability that distributions of real numbers are determined by their moments in the sense of the average of x to the k, if you like the probabilist random variable notation, or the integral of x to the k, if you like the more analysis notation. And there's a moment for each k, natural number 0, 1, 2, ... And this is as long as the moments, those averages don't grow too quickly. All right, so there's some hypothesis on how big the moments can be growing, and as long as they don't grow too quickly, then the moments determine them. And our perspective is that distributions of objects in a category have moments that instead of being indexed by natural numbers are decorated by objects, k themselves, and they should be the average, you know, number of I wrote here surjections from x, so the random object or x is coming from the distribution to some fixed object. So this is the object k. I write it as a capital K. Sorry, you wanted capital K to be a number field, but I also wanted it to remind us of this little k from the kth moment. All right. And the Sur star, I called it Sur because I'm often thinking about surjections. So this denotes epimorphisms in the appropriate category. So when we work on the moment problem, we work in a very general category, which does not have to even have a forgetful functor to set. So you know, we work with epimorphisms, but in many concrete examples like groups, we can think of those just as surjections. And the thing that I say here is sometimes clear and sometimes subtle to define is what exact category your object is in, or you should think of it being in. If it has extra structure, how you put that extra structure into a category. Like, for example, maybe your group has some kind of pairing, but those pairings don't map well. There is some subtlety of figuring out sometimes what the right categorical context is to be applying this game, but in this problem there's not. It's just the category of ZP G modules, you know, with no invariance, or that ZP G modulo that I'm quoting modules. All right, and these averages, like moments of numbers, are often more accessible than the distribution itself. We have seen this in many, many ways. Certainly for us in our function field theorems, this is the case. On the number field side, the few averages we have of class group statistics are all of this form. This is that these averages are somehow the most accessible kind of averages. And of course, that's true in the classical sense. That's why people use moments to study distributions of numbers, is because they're often more accessible. And so a uniqueness theorem in the moment problem says that there's at most one distribution with some given moments. That's the uniqueness aspect of the moment problem. And this has been actually applied a lot in arithmetic statistics and statistics of distributions of class groups and Selmer groups of elliptic curves. So maybe the first one that I see in this sort of arithmetic statistics world is of Heath Brown on statistics of Selmer groups of quadratic twists of an elliptic curve. And these uniqueness theorems, so the uniqueness theorem says, okay, if you have certain averages, like if for every k you know this average, then that determines uniquely the distribution. Been used by Fruvi-Includers, by Ellenberg, Venkatesh, and Westerlin, by myself and with my student Wei-Tong Wang and with Nigel Boston and Will Solin and Lebnowski, Solin, and Zimmerman have all like proved, each of these represents someone who had to prove a paper in which a new uniqueness theorem had to be proven for a new, slightly different category, which is part of the reason why we decided we're going to do things very generally over a very general category. But in all of these examples, there was some known distribution with known moments, conjecturally the distribution of the groups arising from arithmetic. So like, for example, in Ellenberg, Venkatesh, and Westerlin's work, which is a Q goes to infinity result about the CLL subgroups of quadratic extensions of FQT or hyperelliptic curves over FQ, they expected the distribution to be given by the Cohen-Lenstra distribution for the distribution of class groups of quadratic fields. So they knew what distribution they were hoping for, and they knew its moments. And then when they saw the moments that they were hoping for, then they said, yes, we got the distribution that we wanted. And this is the case in all of these previous examples. But what happened here was we knew the moments, but we didn't know a distribution with those moments. So that function field theorem that I said that we had those averages, that's where we started. We said, okay, hey, we think we know what the averages are, but there isn't any conjectural distribution with those moments. And so in our moment problem paper, so this is the moment problem for random objects in a category. So we proved that moments determine the distribution, like I said, in a quite general category. But maybe really relevantly for this talk, we give useful formulas for the distribution in terms of moments. Of course, useful maybe is in the eye of the beholder, but one important thing I want in my formulas is to know whether they are zero or not. As you saw here, that was like that was a big use that gave us essentially, being able to have a formula and see whether or not it's zero, in essence, gave us a theorem in the number field case about what class groups couldn't occur, because we knew somehow what the shape of the theorem was, because we knew where the zeros should be. So that's the kind of thing that I mean for useful. Yes, so I say, so for example, in relevant examples, like you can tell when the formulas give zero versus non-zero values. All right, and so this is, okay, sort of going to be a silly example because it's just the example that you've already seen the formulas for. But now it's just, this is a theorem about measures on FPG modules, right? So this is just where we show that the unique, there's a unique measure on FPG modules with these moments, and it's these probabilities. So there's the same formula as you've seen before. And we actually prove stronger than this, but as you see, the slide is already kind of crowded. But we show, in fact, if you have a sequence of distributions whose averages have these, whose moments have these limits, then the distributions themselves must converge to this distribution. So that is a stronger statement than I've written here, which just would make this slide even more crowded, but it's very important in this theory because actually we never have a single distribution in this whole story. It's always like a sequence of distributions as the discriminant is going to infinity or something. So, and again here, you can see, I mean, I wrote, you can see by the shape of the formulas when things are zero. I wrote the formula like this, which you're like, well, that's kind of you just had a special case here, but you can actually see from the shape of the denominators here that if Fi and Fj had gotten bigger than U and I still used this formula, then I would sort of pass through 0 here. And I mean, so what really happens is you get a formula, and then sometimes the factors are 0 and other times they're not. And that's how you can tell 0 from non-zero things. Okay. All right. And yeah, so just a few remarks to end with. So this was all about distributions for non-Galois extensions. But you say, okay, well, or sorry, for Galois extensions. I said everything in for Galois extensions. But if you're interested in non-Galois extensions, for COP subgroups for P not dividing the order of the Galois closure, you can write down very explicitly how the formulas for the Galois case translate into the non-Galois case. So that kind of process for the explicit translation of those formulas is in a paper of mine with Wei-Tong Wang, and we give example of that in the paper with Will. So just for simplicity, I've sort of said everything in the Galois case, but this all applies equally well in the non-Galois case, as long as P does not divide the order of the Galois closure group. And if you want, some people say, well, I know it is a G module structure, but I don't really care. I want to know, how often can you get every finite abelian group? These can be fairly easily pushed forward to distributions on groups, but they just occur sort of then. Now you just have sort of a sum of terms basically over all the different ways that you could have a G module with that underlying abelian group. So they're not, the formulas like don't, you know, they seem to sort of naturally live here, but we show in the paper some examples where you can sort of push them forward and get the explicit distributions. And finally, so we don't consider in this paper pairing or additional data on the class group, but there is some additional data on the class group that in some sense is responsible for what we're seeing. And we are going to explain that more in our next paper that we are working on, which is not just about the class group, but about this sort of non-abelian generalization of the Galois group of the maximal unramified extension. Okay, thank you.